We begin at home, that pale living world wrapped in blue, teeming with breath and thought, suspended in the quiet void. As we rise above Earth, the sky darkens, revealing the moon, ancient and scarred, forever orbiting, a silent witness to our first steps beyond. We pass Mars, red and wistful, a world that might once have known rivers and rain. Beyond lie shattered stones, the asteroid belt, a graveyard of ancient collisions. Then Jupiter looms, vast and roaring, its storms eternal, its moons mysterious and icy, harboring oceans hidden beneath frozen shells. Saturn follows, adorned in rings like a cosmic crown, elegant and haunting. As we pass the outer giants, Uranus and Neptune drift in a haze of methane blue, cold and forgotten. The sunlight fades. We slip past the Kuiper Belt's icy debris, and there, tiny and brave, Voyager 1 drifts into interstellar space, a relic, a message in a bottle, still whispering to the stars from the edge of human touch. But we do not stop. We move farther into the dark, through the Oort cloud, a ghostly halo of comets, waiting for a disturbance that may never come. Beyond that lies true emptiness. We travel for light years. Stars become fewer, colder. We pass by supernova remnants, where suns have died in fire, scattering the elements of life across the cosmos. A black hole bends light like glass warped by heat, its event horizon humming with secrets. We cross paths with quasars, ancient beacons from the young universe, pouring energy across billions of years. Galaxies drift past us, colliding in slow dances that take eons, their stars intermingling, their shapes stretched like paint on a cosmic canvas. Farther still, the glow of creation begins to fade. We approach the edge of the observable universe, 13.8 billion years from where we began. Time itself slows. Space stretches. Here, the oldest light still flickers, echoing from the birth of everything, the afterglow of the Big Bang. And yet, beyond this veil, something stirs. We cannot see it, we cannot touch it, but we feel the pull, the yearning to know what lies past the edge of forever. Is there more beyond this final horizon? Realms. Beyond time, other universes, hidden truths waiting in the dark? We do not know. Not yet. But this journey from Earth to eternity is proof that we will always ask, always wonder, always reach. Because beyond the stars, beyond space, beyond time may lie our greatest discovery yet. In the beginning, there was only dusk and silence. Around newborn stars, the chaos of creation unfolded. Clouds of gas and rock spinning wildly in luminous disks, colliding, breaking, binding again. In this vast silence, gravity was the invisible hand, drawing together matter with the quiet patience of eternity. Worlds were not built in an instant. They grew grain by grain, pulled inward by a force that does not shout, but waits. This is the music of the cosmos, not of noise, but of movement. The planets began to circle their suns in great arcs, each orbit a note in a song too large for any one mind to fully hear. Gravity carved out order from the chaos. It spun Earth into a cradle where water could flow and life could bloom. It placed Jupiter as a sentinel shielding us from death by It caught our moon and held it close, guiding our tides, balancing our seasons, calming the tilt of our world like a parent steadying a child's first steps. Across the galaxy, other dances emerged. Some stars embraced hot Jupiters that spiraled dangerously close, tugging at the very skin of their parent suns. Others hosted rogue planets, dark, wandering giants cast out of their homes, lost in the black between stars. There are super-Earths and ocean worlds locked in tidal grips around red dwarfs, orbiting in perfect synchrony. forever showing one face to their star, caught in a perpetual sunrise. And still, gravity shapes it all. The rise and fall of worlds, the slingshot arcs of comets, the slow swirl of entire galaxies, the collapsing of matter into black holes where even light cannot escape its grip. But gravity is more than motion. It is memory, relationship, devotion. It is the link between what was and what will be. Without a word, it tells the story of the universe again and again, in loops and spirals and falling leaves. It pulls on us too, in ways we can measure and in ways we cannot. Our oceans rise and fall with its breath. Our bodies grew in response to it. Even our hearts beat in time with the rhythm it first set in motion. We are not separate from this dance. We are part of it. To live is to orbit, to spin, to fall and rise again. The universe does not watch us from afar. It includes us. It holds us. We are not just observers of this cosmic ballet. We are dancers. In the earliest breath of time, when existence itself had barely begun, there was only silence. An endless darkness cradling the seeds of everything that would ever be. Then came the Big Bang, not an explosion in space, but the birth of space itself, a surge of unimaginable energy and light, expanding in all directions, carrying with it the fabric of time, the blueprint of galaxies, and the possibility of stars. In those first chaotic moments, matter struggled to exist. Photons danced wildly in a sea of particles, and gravity began its slow and steady work, pulling, shaping, sculpting the raw universe into order. Over millions of years, what was once a storm of energy cooled and settled into clouds of gas. These clouds clumped, swirled, and collapsed under their own weight until, at last, the first galaxies flickered into being, a faint cosmic heartbeat in the great silence. These early galaxies were small and primitive, but they grew by merging, devouring, and colliding, building the grand structures we now see stretched across the night sky. Spiral galaxies spun into elegant disks, with arms like celestial pinwheels, rich with blue stars and bright nurseries where suns are born. Elliptical galaxies swelled into glowing, rounded masses, their stars older and redder, their history etched into every orbit. Irregular galaxies, shaped by violence and chance, floated like drifting brushstrokes on a canvas too vast to grasp. Some galaxies formed chains and clusters, threading together into filaments that stretched across billions of light years. Webs of starlight connecting the universe like veins beneath the skin of a cosmic giant. In the heart of almost every galaxy lies a secret, a supermassive black hole, invisible but powerful, millions or billions of times the mass of our sun. These black holes do not merely consume, they orchestrate. Their immense gravity guides the rotation of stars, shapes the behavior of gas, and sometimes ignites quasars. Beacons so bright they outshine entire galaxies. Around them swirl the accretion disks, glowing rings of falling matter, marking the edge of time itself. And yet, while these centers pulse with intensity, the galaxies themselves remain serene from afar. Each one a symphony of light, each star a note played in harmony with 100 billion others. To witness a galaxy is to witness time itself. The light from Andromeda, our nearest spiral neighbor, takes over 2 million years to reach us. We see it not as it is, but as it was. A frozen image from a past older than every human civilization. That galaxy, beautiful and vast, is racing toward us at hundreds of kilometers per second. In 4 billion years, it will collide with our Milky Way, and the two will merge in a slow, graceful dance lasting another billion years, forming a new galaxy, perhaps elliptically shaped, perhaps something we have never seen. No stars will crash, But their gravitational paths will warp and tangle, and new stars will be born from the chaos. From this destruction, something greater will emerge, as it always does in the cosmos. We do not merely observe galaxies, we are part of one. The Milky Way is our home, a spiral city of stars where our sun orbits slowly, taking more than 200 million years to complete a single revolution. And within this great turning wheel of light, on the edge of a spiral arm, we live on a fragile world, a pale blue dot orbiting an average star. Yet from this tiny vantage point, humanity has looked up and tried to understand the whole. We have built telescopes that pierce the ancient darkness, capturing images of galaxies so distant their light began its journey before Earth even formed. We have sent probes into the void, carrying greetings for stars that may never reply. We have asked ourselves what it means that we can even wonder at all. What is a galaxy? A collection of stars and gas? A celestial organism? A question made of light? Each one is a story in motion, a living archive of cosmic evolution, a place where new suns are born and old ones fade away. Perhaps they are mirrors, reflecting not just the universe but something inside us. Our hunger for meaning, our loneliness, our beauty. Somewhere, in the glow of a distant spiral, life may look back, wondering the same. We are not just made of stardust, we are made of longing too. The same longing that draws galaxies together in their gravitational embrace. And so the universe sings, in wavelengths and harmonics, in spirals and collisions. The galaxies are its instruments, gravity its rhythm, and light its voice. Their dance is a composition without end, expanding with every passing moment. In the silence between stars, in the dark matter that holds everything together, in the trail of light billions of years old, the cosmos hums with music we are only beginning to hear. The symphony of galaxies plays on, and though we are small, so small, we are listeners in its audience, and perhaps in our questions, in our wonder, in our reaching, we are part of the song. In the still smoking aftermath of the Big Bang, when time was new and space still raw with fire, the universe began to cool. Particles danced into atoms, and atoms into clouds, and from that primordial fog came the first stirrings of form. Gravity, the silent conductor, tugged at the chaos, drawing matter together into luminous structures, proto-galaxies, like sparks caught in a cosmic breath. And so began the grand symphony of galaxies, a music written not in sound, but in light, motion, and time. Across the cosmic canvas, spiral galaxies twirled into being, like elegant pinwheels, their arms laced with newborn stars, while elliptical giants swelled into vast, ancient orbs, glowing faintly with the memory of 1 trillion suns. Irregular galaxies, shattered and strange, drifted like forgotten verses, sculpted by collisions, pulled into knots by invisible threads of dark matter. We pass through glowing star nurseries where light is born in clouds of dust, and peer into the hearts of galaxies where supermassive black holes spin, devouring time, shaping orbits, and holding the luminous whole in delicate balance. Some galaxies cling to each other in gravitational embrace, drawing filaments between them, tidal bridges made of starlight. Others roam alone, exiled from their clusters, drifting like solitary notes lost in the silence between measures. And beyond them all, the Andromeda Galaxy rushes toward us, set on a slow, silent collision with our Milky Way, a cosmic pas de deux that will last billions of years and birth a new form from their union. What is a galaxy, then? A city of stars? A living system? A mirror, perhaps, to some distant life, peering back across the void, wondering if we, too, exist? Each galaxy is a story, a question. a note in an ancient melody written in hydrogen and light. Together, they form a music that never ends, a rising, expanding chorus where gravity is rhythm, stars are harmonies, and the dark between them is the pause that gives the song its soul. The universe plays on, and we, brief listeners, are lucky enough to hear just a whisper of its infinite tune. In the autumn of 1977, from the trembling soil of Earth, a slender silver messenger rose on a pillar of fire, cutting through the blue of our sky and vanishing into the black. Its name was Voyager 1, and in its fragile frame, it carried something more than instruments and wires. It carried a whisper of humanity. The golden record, etched in copper and hope, held our music, our greetings in dozens of languages, the sound of a heartbeat, a kiss, a baby's cry, and the pulse of oceans rolling beneath moonlight. It journeyed past Jupiter, where it beheld storms older than civilization and moons sculpted by ice and fire. It flew by Saturn, tracing the geometry of its rings and sending home images that turned scientists into poets. Then, beyond the last planet, it slipped into the void, where the warmth of the sun fades to a memory and silence rules with a velvet hand. With every kilometer, the radio signal thins, the sunlight dims, and Earth becomes just a pale blue dot. A delicate speck suspended in a sunbeam, fragile and alone in the vast cosmic dark. Voyager has no engine to return, no map beyond the stars it now passes like distant ghosts. It drifts without end, without anchor, yet never without purpose. It is a time capsule and a dream, a message in a bottle, cast into a galactic ocean that may never be answered. It is the echo of a species that dared to look up and say, "We were here." Even now, beyond the edge of our solar system, Voyager still speaks in pulses of light, a fading signal stretched thin by distance but heavy with meaning. It is not just a machine. It is memory. It is longing. It is a whisper from home, carried on the breath of stars. And as it sails deeper into forever, through a silence that no ear can hear, it reminds us that even in the vast loneliness of space, something of us endures, something of us flies. In the beginning there was light, a burning sphere of fury and fusion at the center of our cosmic neighborhood, the sun. A seething giant of hydrogen and helium, its nuclear heart has been shining for over 4.6 billion years, bathing our solar system in warmth and light. Around this star, a family of planets was born from the remnants of its fiery birth. A swirling disk of dust and gas, sculpted by gravity into orbs of rock and ice, clouds and storms. This is our journey. From the blinding brilliance of the sun to the quiet, frozen edges of the solar system, and beyond. We begin with Mercury, a scorched and silent world, the closest to the sun. With no atmosphere to protect it, its surface is baked by day and frozen by night, scarred by craters from ancient collisions. Time here is strange. A single day on Mercury lasts longer than its year. Next, we glide to Venus, Earth's twisted twin. Wrapped in thick clouds of sulfuric acid and a choking atmosphere of carbon dioxide. Its surface, hotter than a pizza oven, hides mountains, valleys, and volcanoes that may still burn. Once possibly Earth-like, Venus now serves as a cautionary tale of runaway greenhouse effects. Then, our own blue marble, Earth, the only known haven for life. Lush with oceans, wrapped in breathable air, alive with forests, deserts, mountains, and billions of living things. It's our home, the only one we know. a planet where the laws of physics made life not just possible, but inevitable. Mars comes next, the red planet. Dry, dusty, and cold, yet it once flowed with water. Riverbeds still trace its ancient past, and frozen lakes sleep beneath its polar caps. We dream of walking here, of planting flags and building homes. Rovers roam its surface today, scouts of a future humanity hopes to claim. Beyond the inner rocky worlds lies the realm of gas giants, and first among them, Jupiter. The largest of all planets, a stormy colossus of swirling clouds, crackling lightning, and a great red spot that could swallow Earth whole. Dozens of moons dance around it, including Europa, where oceans may lie beneath icy crusts. Oceans that just might harbor life. Next, the elegant beauty of Saturn, dressed in rings of ice and dust, the solar system's crown jewel. Its rings stretch wide and thin, shimmering in sunlight, while moons like Titan and Enceladus keep secrets of methane seas and geysers that spray from deep within. Then comes Uranus, tilted so far it seems to roll around the sun on its side. Its pale blue clouds hide icy winds and a strange magnetic field that defies simple logic. Farther still drifts Neptune, the windiest planet in the solar system, where supersonic storms race across deep blue atmospheres. And the Moon, Triton, orbits backward, perhaps a captured world from the dark. Beyond Neptune, the sun's glow begins to fade, and we reach the Kuiper Belt, a realm of icy relics from the solar system's formation. Here lies Pluto, once the 9th planet, now known as a dwarf. Its reclassification sparked debate and wonder, a reminder that science is always evolving. Pluto has mountains of ice, a thin atmosphere, and a heart-shaped glacier that seems to whisper to us through space. But Pluto is not alone. Out here are other mysterious worlds. Eris, more massive than Pluto, Haumea, with its odd shape and fast spin, and Makemake, bright and distant. They, too, are part of our solar family, dancing in the cold dark. Together, they challenge our understanding of what it means to be a planet. And even farther, beyond our reach, may lurk a ghost, the elusive Planet 9, a yet unseen giant whose gravity may tug at the orbits of these distant bodies. If it exists, it is a world shrouded in shadows, waiting to be discovered. Here, at the edge of the known, we find the limits of the sun's influence, the heliopause, where solar wind meets the vastness of interstellar space. And beyond that lies everything else. The galaxy, the stars, the cosmos. The journey from sun to shadows is not just one of distance, it is one of discovery. A reminder that the solar system is alive with stories. Each world a chapter in the epic of our star. And as our telescopes reach farther and our spacecraft fly deeper, the shadows may begin to speak. So we look outward, beyond the planets, beyond the dwarf worlds, into the cold silence of space, and we wonder, what else lies in the darkness? What secrets wait to be known? Jupiter, the mighty guardian of our solar system, stands as the largest of all planets, a true giant among worlds. Towering in both scale and presence, Jupiter is nearly 11 times wider than Earth, with an astonishing equatorial diameter of over 88,800 miles, approximately 142,984 kilometers. It orbits the Sun at a vast average distance of 483.7 million miles, or 78 million kilometers, placing it as the 5th planet from our central star. But Jupiter is far more than just massive. It is a dynamic, churning world of intense beauty and unrelenting storms. bands of clouds colored in shades of cream, rust, and gold race across its surface in opposing directions, creating a mesmerizing marbled atmosphere. The planet's most iconic feature, the Great Red Spot, is a colossal storm large enough to swallow Earth whole. And it has raged for centuries with no signs of ceasing. Beneath its thick layers of gas, Jupiter hides a mysterious interior, possibly a dense core surrounded by metallic hydrogen, where pressures are so great that atoms are squeezed into strange new forms. With a powerful magnetic field and more than 90 known moons, including Europa, Ganymede, and Io, each a world of wonder in its own right. Jupiter is more than a planet. It is a miniature solar system, a protector that deflects asteroids with its immense gravity, and a key player in shaping the evolution of our cosmic neighborhood. In both myth and reality, Jupiter is the king. Vast, ancient, and eternally swirling in the cold depths of space. Uranus, the seventh planet from the Sun, holds a chilling and surprising title. It is the coldest planet in our solar system, even colder than distant Neptune. Though Neptune lies farther from the Sun, it is Uranus that records the lowest temperatures ever measured, plunging to a frigid minus 224 degrees C, 271 DE, dead G. Swathed in pale blue and green hues, Uranus may appear serene from afar, but beneath its calm exterior lies a world of mystery and extremes. Its atmosphere, composed mainly of hydrogen, helium, and a touch of methane, lacks the internal heat seen in other giant planets, leading scientists to puzzle over why it radiates so little energy. Unlike its planetary siblings, Uranus is tipped on its side, rotating almost horizontally, possibly due to an ancient cataclysmic collision, a tilt that causes extreme 42-year-long seasons. Winds whip across its icy clouds at over 500 miles per hour, and the dim sunlight that reaches it barely warms its distant skies. In comparison, Neptune, though farther, maintains a slightly warmer average temperature of around 314 DFC, 353 DFC-F, thanks to its more active internal heating. Yet it is Uranus, the quiet giant cloaked in cold silence, that remains our solar system's most frozen mystery. A lonely sentinel spinning sideways through the dark, with secrets buried deep within its frozen heart. Pluto, once celebrated as the ninth planet of our solar system, now holds a more enigmatic title, a dwarf planet, drifting at the edge of our celestial family. In 2006, the International Astronomical Union, IAU, redefined what it means to be a planet, requiring three key criteria. The body must orbit the Sun, be massive enough for gravity to shape it into a sphere, and, crucially, it must clear the neighborhood around its orbit. It is this third requirement that Pluto could not meet. Residing in the distant Kuiper Belt, a vast region teeming with icy remnants and other small worlds, Pluto shares its orbital zone with countless celestial companions. It lacks the gravitational dominance to sweep its path clean, a cosmic disqualifier in the IAU's eyes. Yet, despite its demotion, Pluto remains a world of wonder. Home to mountains of water ice, a heart-shaped glacier named Tombau Regio, and a complex, dynamic atmosphere. The New Horizons spacecraft's historic flyby in 2015 revealed a frozen world both beautiful and mysterious, stirring emotions across the globe. In truth, Pluto's story is not about what category it fits into, but about how it challenges our definitions. A reminder that the universe is vast, evolving, and full of surprises. Whether planet or dwarf, Pluto continues to inspire curiosity, holding its place in our hearts, if not in the official planetary lineup. Venus, The second planet from the Sun is a world of searing extremes and paradoxes. Though it orbits farther from the Sun than Mercury, Venus holds the title of the hottest planet in our solar system. Its surface, shrouded in a dense, choking atmosphere, composed primarily of carbon dioxide, acts like a vast thermal prison through a process known as the runaway greenhouse effect. This thick atmosphere traps solar heat with relentless efficiency, causing surface temperatures to soar beyond 465 DEGC, 869 DEGF, hot enough to melt lead. Thick clouds of sulfuric acid swirl endlessly above, reflecting sunlight and hiding the tortured landscape beneath. No human-built spacecraft has survived for long on its surface. Landers have succumbed in mere hours. Beneath its golden, cloud-veiled exterior, Venus is a scorched, wind-swept world of volcanic plains and crushed dreams of habitability. It reminds us of the delicate balance required for life and what can happen when that balance is lost. Once thought to be Earth's twin, Venus is now a haunting vision of what Earth might become if we fail to guard our own climate. Its brilliance in the sky is undeniable, a morning star, a goddess of beauty, but behind its radiance lies a tale of hellish transformation. Mercury, the innermost planet of our solar system, is a small and battered world that races around the Sun with blistering speed and ancient silence. Though it holds the title of closest planet to the Sun, Mercury is also the smallest of the 8 major planets, just slightly larger than Earth's moon. At first glance, it appears eerily similar to our moon. A cratered gray sphere scorched by sunlight and shadowed by darkness. But Mercury's story is uniquely its own. With no substantial atmosphere to retain heat, its surface experiences some of the most extreme temperature variations in the solar system. From 430 DGEC, 800 DGF in the daytime, to 180 DGEC, 290 DGGF at night. Its days are long and strange. One full day on Mercury, from sunrise to sunrise, lasts about 176 Earth days, while a year, its full orbit around the Sun, takes only 88 Earth days. Despite being so close to our star, Mercury has pockets of permanent shadow in deep craters at its poles that may hide water ice. A mysterious hint of contrast on a planet thought to be too hot for such a substance to survive. It lacks moons, rings, or weather, but it holds secrets in its dense, iron-rich core and magnetic field. Faint, yet still defiant, Mercury may be small, but it stands as a quiet witness to the Sun's raw power and the chaos of the solar system's early years, whispering a tale of survival against overwhelming odds. Venus, often called Earth's sister planet, is a world of paradoxes. Stunningly bright, yet unimaginably hostile. From afar, it glows like a yellowish-white beacon in our sky, the third brightest object after the Sun and Moon. This brilliance comes not from its surface, but from its dense, reflective clouds, composed largely of sulfuric acid droplets, suspended in a carbon dioxide-rich atmosphere. These clouds trap heat in a runaway greenhouse effect so powerful that Venus holds the record as the hottest planet in the solar system, with surface temperatures soaring to around 475 DEGC, 890 DEGF, hot enough to melt lead. Yet beneath those blinding clouds lies a very different world. The surface is a rocky, reddish-brown wasteland, marked by volcanic plains, crushed mountains, and cracked, ancient lava flows. A crushing atmosphere, 90 times denser than Earth's, bears down on the land below, making the pressure equivalent to being nearly a kilometer beneath the ocean. Venus rotates backward, and slowly, one day lasts 243 Earth days, longer than its year. and its thick atmosphere ensures that night and day blur into a sweltering twilight. No human probe has survived long on its surface, but each glimpse we've received speaks of a planet that was perhaps once Earth-like, only to take a divergent, devastating path. Venus is both beautiful and terrifying, a mirror of what Earth might become if balance is lost. A reminder that even the brightest stars in our sky can hide profound danger beneath their shine. Uranus, the enigmatic green giant, quietly spins on its side at the far edges of our solar system. Often referred to as the green planet, its delicate blue-green hue is caused by methane gas in its atmosphere, which absorbs red light and reflects back the cooler tones of cyan and turquoise. Though it may look serene, Uranus is a world of mystery and extremes. It's the third largest planet in the solar system, yet it's often overlooked, distant, cold, and eerily silent. Temperatures here can plummet to a staggering 224 degrees C, 371 degrees fast, making it the coldest known planet in the solar system, even colder than Neptune, despite being closer to the Sun. Uranus is unique in another way. It rotates on its side, with an axial tilt of about 98 degrees, as if it were knocked over in a cosmic collision long ago. This unusual tilt causes extreme seasonal changes, where each pole gets 42 years of sunlight followed by 42 years of darkness. Its atmosphere is made mostly of hydrogen and helium, with icy materials like water, ammonia, and methane, classifying it as an ice giant. Ringed like Saturn, though fainter, and orbited by a retinue of 27 moons, Uranus drifts slowly, quietly, through the vast twilight of the outer solar system. A frozen sentinel guarding the boundaries of our sun's reach. As humanity's curiosity turned toward the stars, so too did our tools grow sharper. With the invention of the telescope, the once limited list of visible planets expanded. No longer were we bound to just the ancient five: Mercury, Venus, Mars, Jupiter, and Saturn, all named after Roman gods who represented speed, beauty, war, kingship, and time. In 1781, British astronomer William Herschel looked through his telescope and discovered a new world, a pale, distant orb unlike any seen before. At first, it was suggested that the planet be named after King George III, Georgium Sidus. But this was unpopular outside of Britain. Eventually, astronomers returned to the mythological naming convention. However, this time, they reached further back. Not to Roman gods, but to the Greek deity Uranus, the ancient god of the sky and grandfather of most Olympian gods. Uranus remains the only planet named after a figure from Greek mythology, not Roman. Fittingly so, perhaps, for Uranus is a world unlike any other, tilted on its side, spinning slowly beneath a pale green sky. Just as its name broke with tradition, so too does the planet itself. Mysterious, quiet, and cold, orbiting alone at the edge of our awareness. Mars, the red planet, it shines in our night sky like a glowing ember, its rusty hue unmistakable even to ancient sky watchers. Named after the Roman god of war, Mars has long been associated with blood, fire, and conflict, but its red color is not born of myth. It's the result of iron oxide, or rust, covering its surface. Billions of years of weathering have turned Martian dust and rock into a fine oxidized powder that coats the entire planet in a deep rusty red. This iron-rich soil not only colors the Martian landscape, but also defines its character. A cold, dry desert world with towering volcanoes, deep canyons, and the whisper of ancient water. From Earth, Mars appears fiery and bold, but up close, it tells a quieter story. Of a once wetter world, of potential past life, and of a future where humans may one day leave the first footprints beyond Earth. Yarrow, in every grain of red dust lies a question. waiting for us to answer. In the beginning, there was light. From sun to shadows, exploring the planets and beyond, at the heart of our solar system blazes an ancient fire. The sun, a colossal sphere of incandescent hydrogen where nuclear fusion forges light and warmth that has cradled Earth and its siblings for over 4.6 billion years. Every breath we take, every wave that laps ashore, every flower that blooms under an open sky owes its existence to this golden furnace. Its light travels millions of miles to kiss our planet's surface, and yet it is only the beginning of a much greater journey, one that spans the solar system and stretches into the distant unknown. First, we pass Mercury, the closest to the sun, a scorched and cratered world with no atmosphere to hold warmth, where temperatures soar by day and plunge by night. A planet of extremes, whispering tales of ancient collisions and silent sunrises. It's the smallest of the planets, just slightly larger than Earth's moon, yet it holds secrets of a fiery youth. Next comes Venus, shrouded in thick clouds of sulfuric acid. Though further from the sun than Mercury, it burns even hotter. Its atmosphere is a choking blanket of carbon dioxide, creating a runaway greenhouse effect that roasts the surface to over 460 dCc. Beneath the clouds lies a rocky, reddish terrain. But from space, Venus glows yellow-white, a bright and beautiful world, hiding its hostile truth behind a veil of mist. Then we arrive at Earth, our home, a blue marble of oceans and green valleys, of swirling clouds and endless wonder, the only known planet where life thrives, wrapped in a delicate balance of atmosphere, distance from the sun, and magnetic shielding. Earth dances in harmony with the moon, whose gravitational pull stabilizes our axis, giving us seasons and tides and guiding the rhythm of life. Beyond Earth lies Mars, the red planet, its surface coated in rusted iron oxide. Once home to rivers and maybe even life, Mars is now a frozen desert with massive canyons, ancient volcanoes, and dust storms that sweep across plains of memory. But it remains a beacon for human curiosity, a place we may one day call home. Then we leap across the asteroid belt, a ring of rocky debris circling between Mars and Jupiter, the scattered remnants of a planet that never was. And past this rubble, we meet the giant of giants, Jupiter, the fifth planet from the Sun and the largest in our solar system. 11 times wider than Earth, with swirling storms larger than entire continents. Its great red spot has raged for centuries, a violent tempest in an atmosphere of hydrogen and helium. Around it dance dozens of moons. Icy Europa, where oceans lie beneath crusts of ice, volcanic Io, erupting with molten fury, and Ganymede, larger than Mercury, hiding magnetic fields and mystery. Saturn follows, a pale yellow gas giant adorned with shimmering rings made of ice and dust. These rings, vast and elegant, reflect sunlight like cosmic jewelry and encircle a planet of beauty and depth. Like Jupiter, Saturn too holds moons. Titan, wrapped in thick orange haze, with lakes of liquid methane. And Enceladus, a frozen sphere that sprays water into space. Further still is Uranus, tipped on its side like a fallen king, rolling along its orbit. It glows a faint greenish blue, the color of methane, high in its frigid atmosphere. Uranus holds the record as the coldest planet, with temperatures dropping to minus 220 degrees CE. Named not for a Roman god, but the Greek deity of the sky, Uranus is a quiet, icy sentinel at the edge of visibility. Then Neptune, deep blue and storm-swept. Though further from the Sun than Uranus, it burns slightly warmer due to internal heat. Its winds are the fastest in the solar system, racing across a world where sunlight is a distant whisper. Like a symphony's final movement, Neptune's moons, especially Triton, which orbits backwards, hint at past captures and lost histories. But our journey does not end there. Beyond Neptune lies the Kuiper Belt, a vast field of icy relics from the birth of the solar system. Here, in the cold and the dark, drifts Pluto, once the 9th planet, now classified as a dwarf planet. Pluto hasn't cleared its orbital neighborhood, sharing its space with thousands of icy objects, yet it is no less fascinating. With its heart-shaped plains and towering ice mountains, Pluto is a world of frozen beauty. And beyond even Pluto, we find Eris, Haumea, Makemake, other dwarf planets, each telling stories of cosmic migration and planetary evolution. Some scientists whisper of another world, still unseen. Planet 9, tugging gently on the orbits of distant objects, cloaked in shadow, waiting to be found. We now stand on the edge of the solar system, staring into the realm of interstellar space. Far ahead drifts Voyager 1, a tiny craft launched in 1977, carrying with it a golden record, a message from Earth to the cosmos. It has passed the planets, past the heliopause, and now sails silently through the void. Will anyone ever find it? What will they hear in our music, our greetings, our whispers to the stars? And as we look back from the edge of shadows, we realize this journey is not just about planets or moons, gas or rock. It is about us, our need to explore, to understand, to belong. From the sun's warm embrace to the icy silence beyond Pluto, we are part of this celestial story. In the cold darkness beyond Neptune, we are reminded that the solar system is not just a map of worlds, it is a memory of creation, a promise of discovery, and an invitation to keep reaching, to keep wondering, to keep moving through the shadows, guided by the light of a star we call our own. From the endless fabric of the cosmos, where stars are born and galaxies spiral in slow, graceful dances, we begin our journey in the heart of our home, the Milky Way galaxy. A magnificent swirl of stardust and light, our galaxy stretches over 100,000 light-years across, housing billions of stars and untold wonders. But even here, we are not alone. On the vast horizon of deep time, the Andromeda Galaxy slowly approaches, a spiral sister, larger than our own, destined to merge with the Milky Way in a cosmic ballet billions of years from now. Nearby, the Triangulum Galaxy, smaller but dazzling in its complexity, orbits like a silent companion, its luminous arms spinning in harmony. Further still, we glimpse the majestic whirl of the Whirlpool Galaxy, a galactic storm of light and motion, where newborn stars illuminate swirling arms of dust and gas. And hanging like a tilted crown in the cosmic dark, the Sombrero Galaxy glows, its radiant halo and dark lanes of dust resembling a wide-brimmed hat floating through the void. As we leave these grand structures of billions of suns, we descend into the familiar, into the intimate orbit of our own solar system, beginning with Mercury, the smallest and swiftest planet, scorched by the sun yet locked in freezing silence at night. Next comes Venus, cloaked in golden clouds, burning hotter than any planet, its surface veiled by sulfuric skies and crushing pressure. Then Earth, our precious blue world, teeming with life and wonder, protected by oceans and atmosphere where we gaze at the stars and dream of more. Mars follows, dusty, red, and windswept, a silent witness to ancient rivers and potential life long gone. And then we reach Jupiter, the gas giant, the king of planets, whose swirling storms and massive magnetic fields guard a system of moons that may themselves harbor oceans and secrets of life. From galaxies to planets, from the immense to the intimate, the cosmos invites us to explore, to wonder, and to understand. As we drift through the universe, bound by gravity, curiosity, and the eternal question, what else lies out there? Imagine standing beneath a silent night sky, where each star twinkles not just with light, but with the promise of worlds unknown. Beyond our own solar system lie billions of exoplanets, alien planets orbiting distant suns, each a potential harbor for life, each wrapped in a fragile veil of atmosphere. These atmospheric envelopes, often just a few dozen kilometers thick, are the keys to understanding habitability. On Earth, our atmosphere nurtures and protects us, balances climate, and allows life to flourish. Or distant worlds, these invisible layers of gas may whisper the same story. Or a vastly different one. Scientists search for biosignatures, gases like oxygen and methane that, when found together, suggest the delicate imbalance that life creates. But detecting such elusive signals across light years is no simple task. Using advanced tools like the James Webb Space Telescope and Hubble, astronomers watch exoplanets as they transit their stars, capturing the faint starlight that filters through alien skies. That light, etched with the fingerprints of molecules, reveals secrets: clouds of water vapor, hazes of methane, hints of carbon dioxide or ammonia. These observations allow us to build atmospheric portraits, mapping temperatures, pressure, and even winds and storms on worlds we cannot yet touch. Some planets, like Venus, teach us caution, with runaway greenhouse effects turning them into ovens, while others, like Mars, show us the dangers of thin, fragile atmospheres. Among the exoplanets, we look most closely at those in the habitable zone, the sweet spot around a star where temperatures allow liquid water to exist. But water is just the beginning. Scientists now model entire climate systems, test for seasonal variations in gases, and examine spectral features for signs of complex chemistry. Methane, a gas often linked to life, is carefully scrutinized. Could it be from volcanic vents? Or is something alive exhaling into the sky? Clouds made not of water but of iron, silicates, or sulfur drift across some alien horizons, changing what we know about planetary weather. And thanks to new technology like adaptive optics and thermal emission spectroscopy, we're beginning to directly image some of these worlds, catching glimpses of their glowing atmospheres and mysterious composition. Every new discovery pushes us further, beyond mere detection, toward understanding. We stand on the edge of a new era, where future missions like LUVOIR and Habitable Worlds Observatory may finally identify a planet with breathable air, flowing water, and perhaps even the faint scent of life. Yet caution remains. Many signals can mimic life, and nature is full of surprises. Still, we listen. Astrobiologists closely study the complex relationship between atmospheric composition, radiation levels, and the presence of greenhouse gases to understand how life might adapt across diverse planetary environments. One of their most powerful tools is spectral analysis. When an exoplanet passes in front of its star, a process called transit, starlight filters through the planet's atmosphere. During this moment, specific gases absorb certain wavelengths of light, creating a unique spectral fingerprint. By examining these patterns, scientists can detect vital elements like water vapor, carbon dioxide, and methane. Emission spectroscopy, another key method, studies the light emitted directly from a planet, especially during secondary eclipses when the planet disappears behind its star. This technique has been crucial in analyzing hot Jupiters, large gas giants that orbit close to their stars, revealing their intense atmospheric activity. As telescope technology evolves, high-resolution spectroscopy has emerged as a groundbreaking method, providing deeper insight into the atmospheres of distant worlds and increasing our chances of identifying habitable environments. Methane, in particular, has become a focal point in the search for life. On Earth, this gas is often produced by biological processes, like the digestion by microbes or animals. Detecting methane on exoplanets, especially when found alongside oxygen, could point toward active biological systems. This is because methane and oxygen naturally react and destroy each other, meaning both must be continuously produced to exist together. However, methane can also originate from non-living processes such as volcanic activity, so it's essential for scientists to interpret findings with caution by analyzing additional atmospheric markers. Mars has already shown seasonal methane variations, possibly hinting at geological or biological sources. But the mystery remains unsolved. To uncover more answers, scientists rely on telescopes like the James Webb Space Telescope, JWST, which can detect faint traces of gases in distant exoplanet atmospheres. These tools help us identify planets that may support life by analyzing key factors such as temperature and pressure, both critical for maintaining liquid water. While Venus, with its thick, toxic atmosphere, is far too hot, and Mars is cold and dry with a thin atmosphere, both planets offer valuable insight into the range of planetary habitability. Earth, nestled in the habitable or Goldilocks zone, has just the right balance of temperature and pressure, making it ideal for life. The study of alien atmospheres also depends heavily on spectroscopy, which allows scientists to decode a planet's air by observing how light interacts with it. They can even track a planet's own emitted light, or use infrared to detect cooler gases. A planet's distance from its star plays a major role in whether it retains an atmosphere or supports water. Too close, and it may become scorched and airless. Too far, and it may freeze into a lifeless rock. The perfect balance offers the best chance for life-sustaining conditions. Understanding where life might exist also requires a deep dive into biosignatures, indicators of possible biological activity. Spectrometers on space telescopes search for chemical patterns like isotope ratios, seasonal fluctuations, and trace gases such as ozone or methane. For instance, ozone forms on Earth through photosynthesis and helps shield the surface from harmful radiation. Its presence on another planet could hint at photosynthetic life, especially if it appears alongside methane. Because these gases typically react and cancel each other out, their simultaneous presence would strongly suggest an ongoing biological process. Despite our progress, studying exoplanets remains immensely challenging. The light from distant planets is faint and often overpowered by their parent stars. Even with advanced instruments like JWST or Hubble, only a limited number of planets can be observed, often requiring them to align perfectly for transit events. Moreover, stellar flares or sunspots can interfere with measurements, and many atmospheric models are based on Earth's systems, which may not apply to alien environments. Some planets orbiting red dwarf stars may also be bombarded with intense radiation, further complicating studies. To overcome these barriers, scientists are preparing for the next generation of observatories. Telescopes like the extremely large telescope in Chile and ESA's Ariel mission will give us unprecedented access to the temperature, chemical makeup, pressure, and cloud patterns of exoplanet atmospheres. These missions promise to deepen our understanding of how planetary atmospheres form, evolve, and, perhaps most excitingly, whether they can sustain life. Clouds also play a crucial role in shaping planetary environments. On Earth, they regulate temperature by reflecting sunlight or trapping heat. On gas giants, Clouds may be made of ammonia or water vapor, while on hot, rocky planets, they might consist of silicates or sulfur. These cloud compositions influence everything from surface conditions to chemical reactions that could spark life. Ozone, again, stands out as a powerful biosignature. It forms through biological oxygen production and breaks down quickly unless replenished. Another sign that life may be involved. The combined detection of ozone and methane, in particular, creates one of the strongest signals of potential life, as this dynamic balance is nearly impossible to maintain without living systems. Ultimately, the search for life among the stars is a race between our curiosity and our technology. Each new discovery brings us closer to answering the age-older question, are we alone in the universe? With each new telescope, every new planet discovered, and every spectral line decoded, we take another step toward finding out. With thousands of exoplanets already discovered and countless more awaiting confirmation, scientists must prioritize their search by focusing on those worlds most likely to support life, particularly those in the habitable zone, where temperatures may allow liquid water to exist. To understand these distant planets, researchers rely heavily on advanced simulations rooted in the laws of physics and chemistry. These computer models allow scientists to reconstruct the potential conditions on exoplanets based on limited observational data, considering factors like temperature, pressure, and atmospheric composition. For example, when light from a distant star passes through a planet's atmosphere during a transit, simulations help interpret how gases like carbon dioxide or water vapor interact with that light, revealing insights into the planet's heat distribution, weather systems, and even the likelihood of clouds or high-speed winds. Particularly important is understanding how different stars influence their planets. Young stars can emit intense ultraviolet radiation, capable of breaking apart atmospheric molecules or stripping entire atmospheres over time. Simulating these interactions enables scientists to predict whether a planet can retain a stable atmosphere or if it is at risk of atmospheric loss. Adding to the precision of these studies, artificial intelligence and machine learning now play an essential role. Algorithms, trained on vast data sets, help improve predictions about how exoplanet atmospheres behave under various conditions. These AI-driven models evolve as new data arrives, refining future observations and deepening our understanding of planetary habitability. Yet, knowing the atmosphere is only part of the equation. Surface conditions, such as temperature, pressure, and geological activity, are equally critical. A rocky planet too close to its star might suffer extreme heat and lose its atmosphere, while one in the habitable zone with active volcanism might maintain a rich, evolving environment. Oceans, dry deserts, or volcanic plains all shape atmospheric chemistry in unique ways. For example, a carbon dioxide-rich atmosphere could indicate active volcanism, while the presence of both oxygen and methane might point to biological or complex chemical processes. Beyond surface and atmospheric interactions, a planet's magnetic field is vital to its long-term habitability. Like Earth's, a strong magnetic field can protect the atmosphere from being stripped away by stellar winds and cosmic radiation. Without this protection, essential gases could be lost over time, rendering the surface uninhabitable. A magnetic field also helps a planet retain lighter gases like hydrogen and suggests geological activity, such as a molten core or tectonic movement, which further supports atmospheric stability and the cycling of nutrients crucial for life. The presence of volcanism is another key factor. Volcanic eruptions release greenhouse gases like carbon dioxide and water vapor, contributing to climate regulation and atmospheric pressure. On smaller planets, volcanic activity might even replenish gases lost to space. Depending on the type of eruption, These processes can warm the planet, influence weather systems, and alter atmospheric chemistry, creating conditions that might support life. Stellar radiation. Its type, intensity, and variability also shapes planetary environments. High-energy radiation can break apart atmospheric molecules like water vapor, causing vital elements such as hydrogen to escape into space. This gradual atmospheric loss can transform a once habitable world into a barren rock. Planets orbiting cooler stars, on the other hand, may better retain their atmospheres and develop more stable climates. A planet's distance from its star also dictates whether it undergoes a runaway greenhouse effect or freezes into an icy wasteland. All of these factors, climate, radiation, surface activity, and atmospheric composition, are deeply interwoven and essential in evaluating a planet's habitability. Scientists also focus on specific planet types, such as super-Earths, rocky planets larger than Earth but smaller than Neptune. These planets may have dense atmospheres, stable temperatures, and potential surface water. Researchers search for water vapor, oxygen, and methane, as well as cloud formation and greenhouse gases, to assess their potential for life. Magnetic fields and volcanism further increase their habitability. Even gas giants like Jupiter are considered in the search for life, not on their surfaces, but within their upper atmospheres. Complex weather systems, deep pressure zones, and the presence of molecules like methane or phosphine suggest that microbial life might survive in these extreme conditions. One of the strongest indicators of possible life is chemical disequilibrium, when atmospheric gases appear in combinations that wouldn't naturally coexist without ongoing processes. On Earth, oxygen and methane co-occur because living organisms continually replenish them. If scientists observe similar imbalances on distant worlds, it could point to active biological systems. However, alternative sources like volcanic activity must be carefully ruled out, which is why context and layered analysis are critical. Maintaining an atmosphere is key to life. An atmosphere regulates surface temperature and blocks harmful radiation, but intense stellar activity or proximity to a star can strip it away, especially on smaller planets with weaker gravity. The presence of a magnetic field helps prevent this atmospheric escape, as seen on Earth, while its absence, like on Mars, can lead to atmospheric loss and diminished habitability. Some exoplanets, like Proxima Centauri b and TRAPPIST-1e, orbit within their star's habitable zones and may retain thick atmospheres capable of supporting water. K218b has shown signs of water vapor, and GJ357d has favorable conditions for life, while even gas giants like WASP-39b contribute valuable insights into atmospheric evolution. Transit photometry, a technique used to study exoplanet atmospheres, measures the light that filters through a planet's atmosphere during a transit. By examining the wavelengths absorbed, scientists identify the gases present, like methane, oxygen, and water vapor. Over time, repeated observations can reveal seasonal shifts or dynamic weather systems, all offering clues about a planet's potential for life. The discovery of phosphine gas on Venus, a molecule typically associated with life in oxygen-free environments on Earth, further challenges our assumptions and expands the range of environments that might support life. Venus and Mars continue to be critical in shaping atmospheric models. Venus, with its dense, toxic atmosphere and runaway greenhouse effect, shows how proximity to a star can transform a planet into a hostile world. Mars, with its thin atmosphere and cold surface, offers a case study in atmospheric loss. Both worlds provide key lessons for modeling exoplanets, especially super-Earths, and understanding seasonal changes in temperature, atmospheric chemistry, and potential biosignatures. By analyzing photochemical reactions driven by starlight, such as ultraviolet-induced breakdown of gases, scientists can predict how atmospheres evolve. Telescopes like the James Webb Space Telescope allow us to detect faint chemical signals, improving our ability to distinguish between biological and geological sources of gas. Distinguishing real biosignatures from noise requires careful statistical analysis, like Bayesian inference and Markov chain Monte Carlo methods, alongside laboratory experiments simulating exoplanet atmospheres. Peer-reviewed research ensures credibility and helps refine predictive models. Tidally locked planets, despite extreme temperature differences, may harbor habitable regions if their atmospheres are thick enough to redistribute heat effectively. Spectroscopy helps classify atmospheres as oxidizing or reducing, while climate models consider how extreme weather, greenhouse effects, or atmospheric escape influence planetary evolution. Ultimately, understanding exoplanet atmospheres is a multifaceted challenge, requiring precise observation, sophisticated modeling, and a deep understanding of how planetary systems interact. From magnetic fields to volcanoes, from stellar radiation to chemical signatures, every detail contributes to our search for life beyond Earth. And with each step forward, we move closer to answering the timeless question, are we alone in the universe? We watch, because the study of exoplanet atmospheres is not just a scientific challenge, it's a deeply human journey. It bridges astronomy and biology, chemistry and curiosity, and it asks a question that echoes through time and space. Are we alone? Could there be another planet beneath another sun, with beings looking back, asking the same? As we peer into the cosmic dark with telescopes sharpened by centuries of wonder, we move closer to that answer. In every whisper of methane, every flicker of filtered starlight, there may lie the breath of life, waiting to be discovered in the quiet, distant skies of alien worlds. Have you ever looked up at the stars and wondered whether we are truly alone in the vastness of space? As telescopes grow more powerful and science more precise, that question is no longer just philosophical, it's becoming testable. Today, scientists are reaching across unimaginable distances, searching the atmospheres of alien worlds for signs of life. Instead of rockets, we use light. When a distant exoplanet passes in front of its star, some of the starlight filters through its atmosphere. Molecules in that air absorb specific wavelengths of light, leaving behind chemical fingerprints that we can detect from Earth. This technique, called spectroscopy, allows us to identify gases like water vapor, carbon dioxide, methane, and oxygen on planets many light years away. And it's not just the presence of a single gas that excites scientists, it's the combinations. On Earth, life produces a mix of gases that don't easily coexist, such as methane and oxygen. Spotting such mixtures on a distant planet could suggest something extraordinary is happening, perhaps even biology. But atmospheres are complex. Methane, for instance, might come from microbes or from volcanoes. That's why researchers are cautious, combining data with computer models, geological insights, and what we know from Earth to build a fuller picture. Instruments like the James Webb Space Telescope are now giving us our clearest views yet, peering deep into the clouds of exoplanets hundreds of trillions of miles away. And more advanced observatories are coming, like the extremely large telescope and the European Ariel mission, designed to analyze atmospheres in richer detail, measuring temperature, pressure, cloud particles, and chemical reactions with extraordinary sensitivity. Clouds themselves are key players in this search. On some planets, clouds may be made of water vapor or ammonia. On others, they might be toxic, metallic, or even made of glass. These clouds affect radiation, heat flow, and chemical composition, all of which shape whether life could possibly exist. Ozone is another vital clue. On Earth, it forms from oxygen created by living organisms. So if we see ozone along with methane on another world, it could be the closest thing to hearing life whisper from across the stars. But even with these tools, we face limitations. Some planets rarely pass in front of their stars. Others are shrouded in haze or orbit stars too bright to filter out. And there's always the risk of focusing too much on Earth-like life, when alien life might not play by Earth's rules at all. Still, we push forward, combining telescope data with field work here on Earth, studying ancient ice, extreme deserts, deep ocean vents, to understand how life interacts with its environment. These lessons help us read the skies of distant worlds more wisely. We've learned that habitability is not just about being the right distance from a star, but about having the right atmosphere, climate, chemistry, and astrobiologists around the world are diving deep into the mysteries of distant worlds, studying how life might adapt to a variety of alien environments by examining atmospheric conditions, radiation levels, and the presence of greenhouse gases. One of the most powerful tools in their arsenal is spectroscopy, a technique that analyzes light passing through a planet's atmosphere. When an exoplanet transits in front of its star, the starlight filters through the planet's atmosphere, and certain gases absorb specific wavelengths, leaving behind unique spectral fingerprints. These patterns reveal the presence of molecules like water vapor, carbon dioxide, and methane, gases that could hint at life. Emission spectroscopy goes further by analyzing the light emitted directly from a planet, especially during secondary eclipses when the planet disappears behind its star. This method is particularly effective for studying hot Jupiters, gas giants that orbit extremely close to their stars. Scientists are also turning to high-resolution spectroscopy to gather incredibly detailed information about exoplanet atmospheres, enabling them to distinguish between biological and non-biological sources of gases. Among the most intriguing of these gases is methane, which on Earth is often produced by microbial life in wetlands or inside animal stomachs. When methane is detected alongside oxygen, two gases that typically react and cancel each other out, it raises eyebrows because their sustained presence implies continuous replenishment, possibly by light. However, methane can also originate from geological activity like volcanoes, so scientists must carefully study other chemicals and environmental factors before jumping to conclusions. Mars, for instance, has shown fluctuating methane levels that shift with the seasons, fueling speculation that something active, perhaps biological, perhaps not, is at work beneath its dusty surface. Advanced telescopes, like the James Webb Space Telescope, are revolutionizing this field by enabling scientists to detect atmospheric gases on exoplanets light years away. They study planets located in the Goldilocks zone, where conditions are neither too hot nor too cold, making it possible for liquid water, and maybe life, to exist. But habitability is more than just distance from a star. Pressure, atmospheric composition, and temperature also play a role. Planets like Venus, despite being Earth's twin in size, are inhospitable due to their runaway greenhouse effect, while Mars, cold and dry today, may have once been more suitable for life. By analyzing a planet's light through different methods, such as infrared imaging or observing seasonal gas changes, scientists gain insights into its atmospheric makeup. Isotope ratios, like carbon-12 to carbon-13, chemical patterns, and even clouds play a part in the puzzle. On Earth, clouds regulate temperature and can support life by driving chemical processes. On exoplanets, clouds made of silicates or ammonia could either protect or hinder life, depending on their composition. Ozone, another key biosignature, forms from oxygen, a byproduct of photosynthesis, and serves as a protective layer against harmful radiation. If ozone and methane are found together, that's a powerful clue that life could be sustaining both gases. Still, these discoveries are incredibly challenging. Exoplanets are far away, their light is faint, and the signals from their atmospheres are often drowned out by their bright host stars. Many of our current instruments lack the precision needed to capture these faint whispers from other worlds. Additionally, many atmospheric models are based on Earth's conditions and may not apply universally. Red dwarf stars, which are common hosts of exoplanets, emit intense radiation that can strip away atmospheres or complicate observations. But hope is on the horizon. New and upcoming missions, like the extremely large telescope in Chile and ESA's Ariel mission, promise unprecedented insight into exoplanet atmospheres. These instruments will allow us to study temperature, pressure, cloud types, and chemical compositions across a wide range of worlds. By observing light across multiple wavelengths, from ultraviolet to radio, we'll refine our models and narrow down the list of planets that could potentially harbor life. The search for life beyond Earth is one of the most profound scientific endeavors of our time. Each data point brings us closer to answering a question that has captivated humanity for centuries. Are we alone in the universe? As we build better telescopes, develop smarter models, and refine our understanding of life's signatures, we inch ever closer to uncovering that answer. Not just in distant galaxies, but perhaps on a nearby world orbiting a familiar star. Exploring life beneath the ice, the hidden oceans of Europa, Enceladus, and beyond. In the vast reaches of our solar system, far beyond the traditional habitable zone, lie some of the most intriguing candidates for extraterrestrial life. Not planets, but icy moons. Europa, Enceladus, and Ganymede, among others, may harbor vast subsurface oceans beneath their frozen crusts. These oceans, warmed not by sunlight but by tidal forces and geological activity, could create the conditions necessary for life. Scientists have discovered that these moons are more than just frozen worlds. For instance, Enceladus, a moon of Saturn, ejects towering plumes of water vapor and ice from cracks near its south pole. These geysers, analyzed by NASA's Cassini spacecraft, revealed organic molecules and salts, key ingredients for life. Similarly, Europa, one of Jupiter's largest moons, exhibits surface features suggesting a subsurface ocean, possibly enriched with minerals from its rocky seafloor. This mineral-rich water may circulate through hydrothermal vents, echoing the environments found near Earth's deep-sea volcanic ridges, where life thrives without sunlight. The presence of such oceans challenges our previous assumptions about where life can exist. Traditionally, scientists focused on the Goldilocks zone, the area around a star where conditions are just right for liquid water on a planet's surface. But these icy moons prove that geothermal heat and chemistry, not just proximity to the sun, could support life in otherwise frozen and hostile regions. Beneath the ice, microbial life, if it exists, would face extreme conditions: high pressure, freezing temperatures, and perpetual darkness. Yet Earth provides compelling examples of extremophiles that thrive in similar environments, from bacteria living in Antarctic lakes beneath miles of ice, to organisms that flourish around hydrothermal vents in the deep ocean. These analogs suggest that life on icy moons could evolve unique survival strategies such as antifreeze proteins, biofilms, or chemosynthesis, relying on chemical energy instead of sunlight. Supporting this idea, tidal heating plays a central role in keeping these oceans liquid. As moons orbit their giant host planets, gravitational forces flex and compress their interiors, generating frictional heat. This process powers volcanic activity on Io, the most volcanically active moon, and drives oceanic heating on Europa and Enceladus. On Enceladus, these forces crack the ice, allowing plumes of water and organic compounds to escape, providing researchers with a rare, direct glimpse into a hidden ocean. without needing to drill through miles of ice. Advanced missions like NASA's Europa Clipper and ESA's JUICE, Jupiter ICI moons, are set to revolutionize our understanding of these icy bodies. The Clipper will orbit Europa, analyzing its surface composition, magnetic fields, and potential plume activity. JUICE will study Ganymede, Callisto, and Europa. Meanwhile, NASA's Dragonfly mission will fly a rotorcraft across the surface of Titan, Saturn's largest moon, to study its rich organic chemistry and search for signs of prebiotic or biological activity. To complement these missions, scientists are recreating subsurface ocean conditions in laboratories on Earth. High-pressure chambers simulate the crushing depths of icy oceans, while extreme cold, chemical mixtures, and nutrient supplies model their potential chemistry. Sophisticated imaging tools help researchers observe how microbes could survive, adapt, or evolve under such conditions. Salts play a particularly crucial role in subsurface habitability. They lower the freezing point of water, stabilize ocean chemistry, and provide vital ions like sodium and chloride. These compounds not only support cellular functions, but also create energy gradients that could fuel metabolic processes, paralleling Earth's oceanic systems. Should life exist beneath the icy crusts, it may resemble deep-sea life on Earth. Slow-growing, low-energy organisms that communicate chemically or electrically rather than visually. Without light, photosynthesis is off the table, making chemosynthesis, deriving energy from chemical reactions, the primary candidate for biological energy production. These environments could support bioluminescent organisms, flexible body structures, and ecosystems vastly different from any found on the surface. Detecting such life won't be easy. Astrobiologists rely on biosignatures, chemical clues that hint at biological processes. These include specific organic molecules, isotopic imbalances, and patterns of molecular asymmetry. Missions aim to capture plume samples or analyze ice and ocean compositions directly to distinguish between biological and non-biological sources. Beyond the science, there are ethical and planetary protection concerns. To avoid contaminating pristine ecosystems, spacecraft must adhere to rigorous sterilization standards. The idea of discovering life raises philosophical questions about humanity's role in the universe, the rights of alien life forms, and the ethics of exploration. Artificial intelligence and new technologies are essential to overcoming the challenges of deep space exploration. AI-powered rovers and submersibles can operate independently in extreme environments. Low-light solar panels and radioisotope thermoelectric generators will power missions where sunlight is scarce. Laser communication systems promise to enhance data transmission from these distant worlds. Looking ahead, international collaboration will be vital. Missions like Cassini-Huygens and Galileo have shown the value of pooling resources and knowledge. The search for life on icy moons is not just a scientific endeavor, it's a global quest that unites us in our curiosity about the cosmos. The moons of Europa, Enceladus, and Ganymede hold the promise of transforming our understanding of life itself. If we find even the simplest organism beneath the ice, it will prove that life is not a cosmic rarity, but a natural consequence of the universe's chemistry. And that realization would echo far beyond the icy reaches of our solar system, touching on who we are, where we come from, and where we might go next. China's ascent to the moon. In the grand saga of human exploration, the quest to unlock the secrets of the cosmos has long been led by the world's most technologically advanced nations. These missions are more than scientific pursuits. They are bold expressions of curiosity and ambition, revealing the mysteries of space while reshaping our understanding of the universe and ourselves. Among the rising giants in this celestial endeavor is China. Over the past few decades, China has emerged not just as a competitor in the modern space race, but as a force rewriting the narrative of lunar exploration. From the delicate descent of robotic rovers to the successful retrieval of ancient lunar soil, China's achievements are redefining what's possible in space science and exploration. Its most recent missions have garnered global attention, not just for their technological precision, but for their potential to reshape humanity's future beyond Earth. Physicist and futurist Dr. Michio Kaku has remarked on the profound scientific implications of these discoveries. He believes that China's breakthroughs, particularly in lunar geology, could catalyze the next phase of human expansion into space. China's ambitions extend far beyond the moon's surface. The nation has boldly declared its intent to send astronauts to the moon by 2030. This announcement has ignited imaginations and captured the attention of scientists, governments, and space enthusiasts across the globe. Far from a sudden leap, this mission reflects a strategic, decades-long investment in aerospace technology, international collaboration, and scientific research. China's space legacy began in 1964, when it launched its first rocket carrying white mice as a biological experiment. The successful return of that capsule proved that China could contribute to the larger scientific community. By 1970, China launched its first artificial satellite, Dongfang-Hong-1, marking its formal entry into the spacefaring world. The early 2000s brought even greater achievements. In 2003, China became the third nation, after the US and Russia, to send a human into space using its own rocket technology. Astronaut Yang Liwei orbited Earth aboard the Shenzhou 5 spacecraft, spending over 21 hours in space. This milestone inspired a new era of crewed space flight and positioned China among the elite in global space programs. Then came the moon. In 2007, China launched Chang'e-1, its first lunar orbiter. It entered the moon's orbit just 12 days after launch, setting the stage for future missions. Chang'e-2 followed in 2010, advancing the nation's orbital and imaging capabilities. 2013 marked a historic milestone. China became the first country in nearly 4 decades to achieve a soft landing on the moon, as the Chang'e 3 lander and U-2 rover touched down. But it was Chang'e 4 in 2019 that would make history. For the first time ever, humanity reached the far side of the moon, a region shrouded in mystery and untouched by previous missions. There, the mission uncovered tiny glass spheres, remnants of ancient meteorite impacts, offering clues to the moon's violent past and hints of its potential resources for future human use. With its eyes firmly fixed on the future, China now plans to establish a permanent lunar research station by 2035 in collaboration with Russia. This ambitious project will include 5 major facilities and 9 modules to support long-term crewed missions and scientific research. Designed as both a science hub and a stepping stone to deeper space, this station could one day be humanity's foothold on another world. Technological challenges remain. The moon's far side is in permanent radio shadow, making communication with Earth difficult. To overcome this, China launched a dedicated relay satellite, Jiao, ensuring uninterrupted contact between mission control and its robotic explorers. And the discoveries keep coming. In a joint announcement by the China National Space Administration and the China Atomic Energy Authority, scientists revealed the discovery of a brand new lunar mineral, West Changesite. Found within samples retrieved by Chang'e 5, China now joins the US and Russia as the only nations to have identified new minerals on the moon, deepening our understanding of its complex geology and evolution. But China's ambition is not limited to the moon. The Tianwen-1 mission to Mars, which successfully placed both an orbiter and a rover on the red planet, signals a major leap into interplanetary exploration. According to Michio Kaku, this achievement places China at the forefront of a new era, where missions to Mars, asteroids, and even deeper into the solar system may become increasingly common and potentially collaborative. Kaku envisions a future where humanity, armed with breakthroughs in physics and propulsion, might one day travel through the cosmos at will. Concepts once relegated to science fiction, like interdimensional travel and artificial gravity, could become reality in the centuries ahead. But, he cautions, the universe must remain a realm of peace. Revising outdated treaties and establishing global agreements will be critical as nations expand their presence beyond Earth. For now, China's lunar program stands as a testament to scientific ambition, discipline, and vision. With each rover it lands, each sample it retrieves, and each mystery it uncovers, China adds to the story of human discovery. One that stretches from Earth's cradle to the stars. As we watch China's path unfold, one thing is clear. The moon is no longer a silent observer in the night sky. It is becoming a canvas for international exploration, cooperation, and competition. And in this unfolding chapter of space history, China's role is not just prominent, it is pivotal. Today's pivot. The moon has always called to us, a luminous reminder of how far we've come and how far we've yet to go. Through China's remarkable journey, we are reminded that exploration is not just about rockets and rovers. It's about vision, it's about courage, and above all, it's about our shared desire to know what lies beyond. In the coming years, as boots return to lunar soil and research stations rise from regolith, we may very well witness the beginning of a new spacefaring era. One shaped not by any single nation, but by the collective dreams of humanity. The moon is no longer out of reach. It is our next horizon. Imagine a journey that begins on Earth and stretches across the solar system, from the scorching surface of Mercury to the stormy clouds of Jupiter, and then ventures far beyond, through the spiral arms of the Milky Way, into the glowing core of the Whirlpool Galaxy, past the mysterious beauty of Andromeda and Triangulum, and toward the distant rim of the universe. Along the way, what secrets might each world whisper to the traveler? What stories do these celestial wonders tell about time, creation, and our place in the cosmos? This is not just a voyage through space. This is the story of our universe. Mercury, the sun's swift messenger. Mercury, the closest planet to the sun, is a world of extremes. Slightly larger than Earth's moon, this rocky planet endures brutal conditions. Daytime temperatures can soar to 430 DEGC, 800 DEGF, while at night, without an atmosphere to trap heat, they plummet to minus 180 DEGC, 290 DEGF. Its heavily cratered surface, scarred by ancient impacts, offers a glimpse into the early history of the solar system. Mercury is small but mighty, a fast-moving messenger that completes an orbit around the Sun in just 88 Earth days. Venus, the hottest planet. Venus may be Earth's twin in size, but it couldn't be more different in character. Shrouded in thick clouds of carbon dioxide and sulfuric acid, it's the hottest planet in our solar system, hotter even than Mercury. With surface temperatures reaching 475 DGC, 900 DGF, Venus is a blazing inferno. Its atmosphere traps heat in a runaway greenhouse effect, and crushing pressures make it inhospitable. From space, Venus appears as a yellowish-white jewel, glowing brightly in our sky. Yet beneath those beautiful clouds lies a volatile and hostile world, Earth. The oasis of life. Our home, Earth, is the only planet known to support life. It's the perfect balance of atmosphere, water, temperature, and magnetic shielding. With vast oceans, flowing rivers, and vibrant ecosystems, Earth is the crown jewel of the solar system. From space, it appears as a blue marble, alive, dynamic, and breathtaking. Earth's journey around the sun brings the rhythm of seasons, while its moon stabilizes our tilt and tides. It is not just our home, it is a rare gem in the cosmic sea. Mars, the red planet. Mars is a cold, dusty desert world, and yet it beckons with promise. Known as the red planet because of its rusty iron oxide surface, Mars holds secrets in its soil. It has the largest volcano in the solar system, Olympus Mons, and canyons that dwarf the Grand Canyon. Evidence suggests that water once flowed across its surface, and the possibility of ancient life still drives exploration today. Mars is a frontier, waiting for the next chapter of human discovery to be written on its red sands. Jupiter, the giant king. Jupiter, the fifth planet from the Sun, is the largest of them all, 11 times wider than Earth, with a diameter of nearly 143,000 kilometers, 88,846 miles. This gas giant is a swirling canvas of storms, most famously the Great Red Spot, a tempest larger than Earth that has raged for centuries. Jupiter's immense gravity shapes the orbits of many celestial bodies and shields the inner planets from asteroids. Its moons, especially Europa with its hidden ocean, may even harbor life. Jupiter is not just a planet. It's a miniature solar system all its own. Saturn, the Lord of the Rings. Saturn is a masterpiece of elegance, encircled by rings of ice and rock that stretch hundreds of thousands of kilometers wide. Though not the only planet with rings, Saturn's are the most magnificent and complex. This gas giant is less dense than water and has over 80 moons, including Titan, a moon with lakes of methane and a thick atmosphere. Saturn captures the imagination with its beauty and mystery, reminding us that space is filled with wonders we are only beginning to understand. Uranus, the tilted ice giant. Uranus is the coldest planet in our solar system, with temperatures plunging to minus 224 degrees C, 371 degree F, colder even than Neptune. It's known as the green planet, due to its pale blue-green hue, caused by methane in its atmosphere. But Uranus is truly unique for its extreme axial tilt. It spins almost on its side, making its seasons last over 20 Earth years. It was also the first planet discovered using a telescope, and the only one named after a Greek god. Uranus, the god of the sky. Neptune, the windy world. Neptune, the farthest planet from the Sun, is a realm of deep blues and fierce winds. It's known for having the fastest winds in the solar system, up to 2,100 km/h, 1,300 mph. Despite being more distant, Neptune is slightly warmer than Uranus. Its rich blue color also comes from methane, and its atmosphere is marked by storm systems and cloud bands. Neptune is a world of chaos and elegance, a beautiful enigma in the outer solar system. Pluto and the Kuiper Belt, the frozen frontier. Once the ninth planet, Pluto was reclassified as a dwarf planet in 2006 because it does not clear the neighborhood of its orbit. It resides in the Kuiper Belt, a region of icy bodies beyond Neptune. Despite its demotion, Pluto remains a fascinating world, home to mountains of ice, a heart-shaped glacier, and a thin nitrogen atmosphere. Its discovery of the mineral tholins hints at organic chemistry and the complex ingredients of life. Pluto reminds us that even small worlds can be rich in story. The Milky Way, our galactic home. Our solar system resides within the Milky Way galaxy, a sprawling spiral of stars, gas, dust, and dark matter stretching over 100,000 light-years wide. From Earth, the Milky Way appears as a river of light in the night sky, a glowing reminder that we are part of something vast and ancient. Within its arms lie billions of stars, some with their own planets and possibly life. The Milky Way is not just our address. It's a dynamic ecosystem of creation and destruction spinning through the universe. Andromeda, the future collision. The Andromeda Galaxy is our nearest galactic neighbor, 2.5 million light-years away and on a slow, inevitable collision course with the Milky Way. Visible to the naked eye under dark skies, it's even larger than our galaxy and contains over 1 trillion stars. One day, billions of years from now, the Milky Way and Andromeda will merge, forming a new supergalaxy. This grand cosmic event will reshape the night sky and remind us of the universe's ever-changing nature. Triangulum and Whirlpool, cosmic beauties. The Triangulum Galaxy, a smaller companion to Andromeda, is the third largest galaxy in our local group and a hub of star formation. Meanwhile, the Whirlpool Galaxy is a striking example of spiral beauty, with perfectly formed arms and a glowing core. Galaxies like these are not just distant lights. They are living tapestries of stars, black holes, nebulae, and gravity spinning through the void. Sombrero Galaxy, the galactic hat. The Sombrero Galaxy, with its bright central bulge and wide dusty rings, resembles a cosmic hat drifting in space. Its unique structure and high luminosity have made it a favorite among astronomers. Located 28 million light-years away, this galaxy serves as a reminder that the universe is filled with diversity and that beauty takes many forms across space. From the blistering heat of Venus to the icy stillness of Uranus, from the rings of Saturn to the spirals of distant galaxies, each stop on this cosmic voyage tells a story of time and matter, of violence and grace, of what it means to exist in the vastness of space. And through it all, Earth stands as a singular haven, a blue beacon among a sea of stars. As we look up into the night sky, we are not just observers. We are part of the universe, born from its dust, shaped by its laws, and drawn ever forward by the promise of discovery. And so, our search continues, not just with telescopes and data, but with imagination and wonder. From the faint glimmer of a star in the night sky to the spectral traces of gases in a distant atmosphere, each discovery brings us a step closer to something profound. Methane, ozone, water vapor, these are more than just molecules. They are cosmic whispers, possibilities etched into the air of far-off worlds. We are now decoding the chemistry of alien skies, searching not only for signs of life, but for understanding of how rare or how common life might be in this vast universe. With every new telescope launched, with every new exoplanet found, we are pushing the limits of what humanity can see and know. Worlds that were once the stuff of science fiction now sit in our databases, waiting to be understood. Planets orbiting red dwarfs, gas giants cloaked in storms, and rocky Earth-like bodies within the habitable zone. They all hold secrets we've only begun to unlock. Yet the search is not easy. Clouds can hide clues, star flares can confuse the data, and many of the signals we seek are so faint they blur into cosmic noise. Still, we persist, because the payoff is enormous. The possibility of finding life beyond Earth. Perhaps someday we will spot a planet with just the right mix of gases, oxygen and methane, ozone and carbon dioxide, existing together in a delicate balance that screams of biology. Or maybe we'll discover a completely new form of life, born under conditions we've never imagined, rewriting the very definition of habitability. Whatever the outcome, the journey changes us. It reminds us that we are a species of seekers, explorers, not just of land and sea, but of the infinite sky above. So as we stare into the dark, scanning for a flicker of familiarity in alien light, we are also looking inward at our own world, our fragile Earth, and our place in this cosmic story. The stars are ancient, but our ability to listen to them is new. And now that we are finally hearing the whispers of distant planets, we must ask ourselves, are we ready for the answer? If you enjoyed this journey through the cosmos and want to explore more wonders of the universe with us, don't forget to like, share, and subscribe. The universe is vast, and our adventure has only just begun. Communicating across interstellar distances is a fascinating and complex challenge that involves astrophysics, engineering, and linguistics. The vast distances, like the 4.37 light-years to the nearest star system, Alpha Centauri, mean signals take years to travel, making real-time conversations impossible. Our Milky Way galaxy is about 100,000 light-years wide, making communication with distant stars almost unimaginable. Current methods mostly use radio waves, which weaken over distance, making it hard to get clear signals. Scientists are exploring advanced technologies like laser communication for more focused, powerful transmissions, but these are still in early development. It's dark out, but a star or a populous island. Space also adds noise and interference from cosmic radiation, complicating signal clarity. Researchers are working on filtering techniques to improve reception. Decoding messages from extraterrestrial civilizations poses another challenge, as we must understand unknown languages, intentions, and contexts. Concepts like math and prime numbers are considered as universal communication tools. The speed of light, about 300,000 km/s, limits communication speed, causing unavoidable delays. Even the closest stars require years for signals to travel back and forth. Signals also weaken over distance due to attenuation and can be distorted by relative motion, the Doppler effect. To ensure message accuracy, redundancy, and error-correcting codes are used. Standard communication protocols help maintain clarity and shared understanding across civilizations. Despite the immense challenges, interstellar communication pushes our understanding of physics, technology, and the universe's vastness. Collaborative space missions often involve multiple spacecraft exploring different parts of the solar system or beyond. For example, signals sent from a Mars rover to Earth can take several minutes due to the distance and relative positions of the planets and ostracism. This delay requires spacecraft to have autonomous systems, as real-time control from Earth isn't possible. In the search for extraterrestrial intelligence, SETI, the speed of light limits our ability to detect signals. Any detected message might be thousands or millions of years old, requiring interpretation in a very different time context. Scientists have explored various methods for sending messages across interstellar space. Radio waves have been the primary method, such as the 1974 Arecibo message aimed at the M13 star cluster, which encoded information about Earth and humans. Laser communication offers a promising alternative by sending focused pulses of light, but detecting these faint signals across vast distances remains a challenge. Physical probes like the Breakthrough Starshot Initiative aim to send tiny spacecraft to Alpha Centauri, traveling at a fraction of light speed to return data in decades. Another theoretical method involves quantum entanglement, which might allow instant communication, though this remains speculative and unproven. Neutrinos, tiny, nearly massless particles, can travel through matter without much interference, making them a potential candidate for interstellar messaging. However, generating and detecting neutrino signals is technologically difficult. Even at light speed, about 300,000 km/s, messages take significant time to reach distant targets. For instance, Voyager 1, the farthest human-made object, requires over 21 hours for a one-way signal to travel. Communication delays also vary within the solar system, such as between Earth and Mars, where signals take 4 to 24 minutes depending on their orbital positions. Space conditions add further challenges. Signals can weaken or distort due to cosmic interference, like solar flares or dense gas clouds. These factors must be accounted for in mission planning and communication system design. The vastness of space and the finite speed of light mean communication with other star systems involves long delays. Sending and receiving a message to Proxima Centauri would take over 8 years round trip. These delays complicate real-time communication and coordination, impacting scientific missions and potential contact with extraterrestrial civilizations. When sending signals across space, there are several challenges besides the huge time delays. Signals weaken and can get distorted while traveling through space, which isn't a perfect vacuum. Cosmic phenomena like microwave background radiation, solar flares, and interstellar dust interfere with signal clarity, causing potential loss or misunderstanding of messages. This signal weakening means messages may arrive incomplete or unclear. Scientists use complex encoding to reduce errors, but this adds difficulty. The delay itself complicates communication. By the time a response arrives, the situation or context may have changed, possibly leading to misinterpretations between us and any extraterrestrial intelligence. Repetitive efforts. Perfectionism causes a massive disruption of schedule, career, intelligence, and time. Cosmic events like supernovae release intense radiation that disrupts radio signals, causing noise or even signal loss. Black holes can bend or distort signals through gravitational lensing, delaying or altering the transmission. Cosmic rays from these events also interfere with satellites and ground communications, requiring robust technology to handle these unpredictable effects. Radio waves are crucial for interstellar communication because they travel far without much absorption or scattering. Specific frequencies like the water hole band 1420166000 are quieter and better for clear signals. Scientists use radio telescopes to both send messages and search for signals from extraterrestrial civilizations, a field called SETI. However, the vast distances make signals weak, requiring sensitive instruments. Additionally, interpreting any received message would be challenging, since alien languages or codes could be completely unfamiliar. In summary, communication with extraterrestrials faces major obstacles: long delays, signal degradation from cosmic interference, and the difficulties of interpreting unknown languages. Despite this, radio waves remain our best tool for attempting contact across the vastness of space. Communicating across space is a huge challenge due to the vast distances and complex physics involved. Space signals mainly travel as electromagnetic waves, like radio waves and light. Low-frequency radio waves travel farthest because they don't lose much strength, while higher-frequency waves scatter or get absorbed more easily. The Doppler effect and the universe's expansion stretch signals over time, making them weaker and slower to arrive. This means messages to distant stars could take thousands of years to reach and might arrive changed or hard to decode. Earth's atmosphere, cosmic dust, and signal weakening over distance all create obstacles. Signals lose strength following the inverse square law, and interference makes detecting faint messages tricky. To tackle this, scientists use powerful telescopes, error-correcting codes, and target specific frequencies. New technologies like laser communication offer faster data rates, while huge radio telescope arrays like the Square Kilometre Array aim to detect even fainter signals. Future innovations such as quantum communication might revolutionize space messaging. Meanwhile, projects like SETI scan the skies, searching for signs of intelligent life. All totally normal, annulus. Though interstellar communication is difficult, advancements keep us hopeful that one day we may send or receive messages across the stars, unlocking secrets of the universe. Interstellar communication and challenges. The idea of using powerful beacons to send messages across the galaxy is gaining interest. However, signal noise, unwanted interference, makes it hard to detect and decode messages over vast cosmic distances. To overcome this, scientists use advanced data encoding, focused lasers, large radio telescopes, and multiple receiver arrays to improve signal clarity. Artificial intelligence helps filter noise, and quantum communication holds promise for secure, potentially instantaneous messaging, though faster-than-light communication remains theoretically impossible. The Great Silence and its implications. Despite many stars and possibly habitable planets, we have yet to detect clear signs of intelligent life, a puzzle known as the Great Silence, or Fermi paradox. Explanations include the rarity of life, self-destruction of civilizations, or use of unknown communication methods beyond our detection. This silence prompts philosophical questions about intelligence and urges humanity to develop better technology and search methods such as SETI. Ethical considerations in contacting extraterrestrials. Reaching out to alien civilizations raises ethical issues. Should we initiate contact? Could it expose them or us to harm? Who decides how to represent humanity? Messages might be misunderstood, causing conflict. Respect for alien autonomy and non-interference, like a prime directive, is crucial. Also, announcing our presence might attract risks, so secrecy versus openness is debated. Quantum cryptography and communication. Quantum cryptography ensures secure communication by detecting any eavesdropping attempts. Measuring a quantum state changes it, alerting the parties involved. This is vital for protecting sensitive interstellar messages. Quantum repeaters will extend signal range, enabling communication across the solar system. Hybrid systems combining quantum and classical methods may offer more reliable networks. Lasers for interstellar communication. Lasers provide focused, clear signals that can travel long distances with minimal interference. Unlike radio waves, they can carry large amounts of data, including images and video. Networks of laser beacons on spacecraft or celestial bodies could relay messages across the galaxy. Targeted laser signals could even enable two-way communication with intelligent exoplanets. Projects like Breakthrough Starshot use lasers for propulsion, highlighting their multi-role potential, selecting target stars and planets. Scientists choose stars similar to the Sun, especially those in the habitable zone where liquid water could exist. Stability and proximity are important for faster and more likely communication. The Drake equation helps estimate how many communicative civilizations might exist. Exoplanets are discovered by methods like transit and radial velocity, with size, composition, and atmosphere analyzed for habitability. Missions like Kepler and TESS have identified thousands of candidate planets, encoding messages for extraterrestrial civilizations. Messages must use universal concepts like math and basic science to overcome language and cultural barriers. For example, the Arecibo message used binary code to describe humanity and our solar system. Simplicity and clarity are crucial to avoid misinterpretation or hostility. Different transmission methods, radio waves, lasers, affect how messages are encoded and received. Philosophical and human significance. This quest reflects humanity's deep curiosity and hope to connect with other intelligent beings in the cosmos. It encourages unity by inspiring us to represent our species thoughtfully. Mathematics, especially prime numbers, is seen as a universal language, likely recognizable by any intelligent life. Universal language through mathematics and physics. Communicating with extraterrestrial civilizations requires a language transcending cultural and linguistic barriers. Mathematics offers a promising universal medium, as mathematical principles are inherent to the fabric of the universe and likely recognizable by any intelligent life. For example, prime numbers. A sequence of pulses reflecting prime numbers could signal intentional communication, showcasing intelligence. The Fibonacci sequence, common in nature's patterns, it could help establish a shared understanding of natural phenomena. Fundamental constants. Constants like the speed of light or Planck's constant represent universal physical laws, offering a shared basis for encoding messages. Binary code. The Arecibo message, sent in 1974, used binary encoding, illustrating the power of simple two-symbol systems in bridging communication gaps. Messages might employ visual formats, diagrams, graphs, or auditory signals, mathematical tones or rhythms, each with unique advantages for interstellar messaging. Challenges of scale and technology. Immense distances. Even the nearest star, Proxima Centauri, is about 4 light-years away, causing years-long delays in message exchange. Expanding universe. Distant civilizations might be moving away too fast for messages to reach them. Vast number of targets. With trillions of galaxies and billions of stars, selecting target stars and habitable planets requires advanced telescopes and methods to detect biosignatures. Signal detection, differentiating genuine extraterrestrial signals from cosmic background noise and human-made interference is extremely challenging. Unknown communication technologies. Alien civilizations might use communication methods beyond our current understanding, potentially making our searches ineffective. Cultural and linguistic considerations. Language diversity. Different human languages have unique structures and idioms, complicating the creation of messages understandable across species. Nonverbal communication. Gestures or expressions that seem friendly to us might be offensive or meaningless to aliens. Different scientific paradigms. Civilizations might have fundamentally different scientific and technological frameworks, complicating message interpretation. Ethical variability. Varied cultural ethics may influence whether and how civilizations choose to communicate or respond. The Fermi paradox and its implications. Despite the high probability of extraterrestrial civilizations, no confirmed signals have been detected. Possible explanations include advanced, undetectable technologies. Civilizations may use communication methods beyond our detection capabilities, such as quantum communication, rarity, or brief lifespans of civilizations. Intelligent life might be extremely rare or self-destruct quickly due to warfare, environmental collapse, or technological disasters. The Great Filter, a hypothesized evolutionary barrier that prevents life from reaching advanced stages of communication and exploration. The Zoo hypothesis suggests advanced civilizations intentionally avoid contact, observing us like a cosmic zoo to allow natural development without interference. Communicating with extraterrestrial civilizations presents many challenges. Using universal concepts like prime numbers or the Fibonacci sequence can help create messages that demonstrate intelligence and establish common ground. Mathematics and physics, including fundamental constants, offer a shared language across the cosmos. However, vast distances cause significant delays. Messages to nearby stars take years to arrive, making real-time conversation impossible. The universe's immense scale and expansion further complicate targeting potential life-bearing planets. Advanced technology and signals beyond our current understanding may also hinder detection. Cultural differences add complexity, as alien communication methods might differ vastly from human languages and expressions, increasing the risk of misunderstanding. Establishing clear, simple, and redundant protocols, often employing binary codes or pictograms, improves the chances of successful communication. Artificial intelligence plays a crucial role by analyzing enormous datasets, distinguishing potential signals from cosmic noise, and modeling communication scenarios. Secure communication requires encryption, error correction, and international cooperation to protect messages from interception and corruption. Finally, ethical questions arise. Advanced civilizations might purposely avoid contact to allow natural development, similar to how humans observe wildlife. Overall, interstellar communication demands patience, clarity, and a deep understanding of both technology and culture to bridge the cosmic divide. In our quest to communicate with intelligent life beyond Earth, we confront an extraordinary challenge, one that spans not just the vast distances of space, but also the profound differences in biology, perception, and understanding. What we consider foundational, such as basic mathematics, or even the concept of time, may not exist in the cognitive framework of an alien species. A message that seems simple to us, like a greeting, could be misinterpreted as a threat. An expression of curiosity might be seen as aggression. The very intent behind a signal could be entirely lost in translation. Encoding data is another obstacle. We rely on binary, visual symbols, or electromagnetic signals. But these may be completely foreign to extraterrestrial senses. They might perceive the universe through dimensions, wavelengths, or cognitive modalities that we can't even imagine, rendering our communication methods obsolete. Even if we manage to send a message, there's the ever-present challenge of cosmic noise, both natural and man-made. From cosmic microwave background radiation to the chatter of Earth's own technology, our signals could easily be drowned out or lost. But the future offers hope. Advancements in quantum communication hold the promise of instant data transfer across vast distances. Unlike electromagnetic waves, which travel at the speed of light, quantum entanglement could allow for real-time conversations between Earth and distant stars. If we can unlock its secrets, imagine sending a message to a distant star system and receiving an answer back without the decades-long delay. It would redefine space and time in the context of communication. Artificial intelligence and machine learning are also revolutionizing our ability to analyze the cosmos. These technologies can sift through petabytes of data from telescopes and space probes, identifying patterns that human eyes might miss, perhaps even detecting the first whisper of an alien civilization. New telescopes, with unprecedented sensitivity, will peer deeper into space than ever before. They'll scan the atmospheres of exoplanets, searching for biosignatures, or even artificial signals. And beyond technology, we are beginning to develop new conceptual languages, communication systems based on universal constants like mathematics, physics, or the structure of atoms. These could form the basis of a shared vocabulary with other civilizations. Visual, auditory, and even tactile modes of communication could merge into multifaceted messages designed to transcend species-specific limitations. A growing network of satellites and space infrastructure may also evolve into a solar system-wide relay, enabling faster communication with spacecraft and outposts. This would serve as a critical testbed for eventual interstellar messaging. Laser-based communication is another emerging frontier. These tightly focused beams can carry vast amounts of data across space with minimal loss, making it possible to transmit images, data, and potentially even video to other star systems. Yet as we prepare to reach out, we must also consider relativity, particularly time dilation. At speeds approaching that of light, time slows down relative to observers. For a crew traveling to Proxima Centauri, just 4 light-years away, a few years might pass aboard their ship, while decades elapse on Earth. This discrepancy complicates message timing, making real-time dialogue nearly impossible. Messages might arrive long after their context is relevant, leading to confusion or miscommunication. If a fast-moving spaceship sends a message back to Earth, the data may arrive years too late, and the crew's current status could already be outdated. Protocols must account for this. Communication strategies need to be asynchronous, predictive, and robust, ensuring that even with long delays, the information remains actionable and clear. Now imagine this complexity scaled up to communication with an alien civilization. If their time perception differs due to biology or physics, even defining a day or year might be an enormous challenge. Organizations like the SETI Institute continue to scan the sky for signs of intelligent life. With powerful radio telescopes and refined detection algorithms, they search for patterns amid the cosmic noise. Historical anomalies like the WOW signal of 1977 remind us how difficult it is to confirm a true alien transmission. Should we receive such a signal, international protocols have been outlined by groups like the International Academy of Astronautics. They call for global cooperation in verifying, interpreting, and deciding whether to respond. But beyond science and protocol lies a deeper question. What should we say? What values do we wish to project as a species? Do we greet with peace, share knowledge, or remain cautious and silent? Philosophers, ethicists, and scientists are all engaged in these debates. They ask, are we ready to be part of a cosmic conversation? And if so, what message best represents humanity's hopes, dreams, and potential? We must also prepare the public. Educational outreach ensures people understand what's at stake and what we might discover. Through media, lectures, and cultural discussion, humanity slowly prepares for the possibility of hearing or being heard across the stars. That response might contain wonders beyond comprehension, a glimpse into alien societies, technologies, even consciousness. They may use radio waves or light beams, or something we've never imagined, perhaps quantum signals sent through space-time itself. The future of interstellar communication is not just a technological journey. It is an exploration of language, time, identity, and our shared place in the cosmos. If an advanced civilization tried to communicate, they might not use words at all. Instead, they could send data packets, mathematical formulas, or even light and chemical signals, forms of communication that reflect their unique understanding of the universe. Their messages might reveal technologies, space exploration experiences, or new theories about physics, like black holes or dark matter. Others might share ethical views, cultural values, or even philosophical ideas. Alternatively, they might choose not to respond at all, possibly seeing us as too primitive or due to their own ethical constraints. Communication could be subtle, such as sending probes or artifacts, rather than direct contact. Receiving such a message would stir emotions across the globe, excitement, fear, or wonder, as humanity reflects on its place in the cosmos. Even without a reply, the vastness of space reminds us that silence doesn't mean we're alone, just that communication is incredibly difficult. This uncertainty can cause existential questions, but it also drives hope and unity in our shared search for connection. Efforts to reach out have been ongoing for decades, from Tesla's 1899 claims to the 1974 Arecibo message and the Voyager Golden Records in 1977. Humanity has attempted to present itself to the universe. These messages include data on DNA, Earth's location, and cultural artifacts, all designed for any intelligent being who might find them. International collaboration is key. Projects like SETI rely on a network of global observatories and researchers. By sharing data, funding, and expertise, nations can overcome the massive challenges of interstellar messaging. Joint missions like NASA's work with the European Space Agency show how global teamwork can accelerate innovation. Working together also helps standardize communication protocols and avoid misunderstandings. Ultimately, the search for extraterrestrial life is more than science. It's a reflection of our curiosity, our unity, and our hope that we are not alone in the universe. Establishing contact with an alien civilization would be a groundbreaking moment in human history. It would reshape our understanding of the universe and confirm that we are not alone. This realization could unify humanity, sparking a new era of scientific exploration and increased investment in space technology, possibly even leading to interstellar travel. If the communication brings advanced knowledge, it might help us solve major global issues, like climate change, energy shortages, or diseases. But if the message suggests hostility or indifference, it could trigger fear, global debate, and strategic planning for planetary defense. How we respond and what we reveal about ourselves carry significant risks, especially if misunderstood by an alien species. Reactions would vary globally. Some nations might welcome the contact, while others could keep it classified or exploit it for power. This could ignite geopolitical tensions, with countries competing for control over alien communication. Philosophically and culturally, contact with extraterrestrials would challenge our ideas of consciousness, intelligence, and the purpose of life. Religions, philosophies, and art would evolve. Some belief systems may adapt, while others may resist or reinterpret their doctrines. The search for extraterrestrial intelligence, SET, uses radio and laser signals to detect alien life, while METI involves actively sending messages into space. But this comes with risks. Revealing our location might attract hostile attention. Some scientists argue for caution, advising that we remain quiet until we better understand what's out there. There are also ethical questions. Would we be imposing our culture or values on other beings? Should we even communicate at all without a global consensus? International collaboration, perhaps through the United Nations, could help create ethical frameworks and strategies for such contact. A society's political climate, cultural values, and scientific priorities heavily influence its stance on interstellar communication. Nations focused on science and progress are more likely to support space messaging efforts. Others, dealing with internal crises, may ignore or reject such endeavors. Cultural traditions, religious beliefs, and technological capabilities also shape responses. For example, storytelling cultures may embrace the opportunity to share their narratives, while more conservative or religious societies may view alien life with fear or skepticism. Future communication methods aim to overcome the vastness of space. Lasers, which can carry more data over longer distances, are being tested. Quantum entanglement, which allows instantaneous state changes between particles, might one day revolutionize how we send messages. Ideas like relay satellites, pulsar-based signaling, and studying fast radio bursts are being explored to improve long-distance space communication. As AI evolves, it may help craft messages that are more universally understandable, transcending human language and logic. Projects like Breakthrough Starshot aim to send laser-propelled spacecraft to nearby stars, making interstellar communication more feasible. As our understanding of physics, quantum mechanics, and artificial intelligence grows, so does our potential to connect with life beyond Earth. Ultimately, the future of interstellar communication will depend on global cooperation, scientific innovation, and ethical foresight. It is a delicate balance between curiosity and caution, between the thrill of discovery and the responsibility it demands. Imagine zooming in on the universe, not just to the scale of atoms or particles, but far beyond, to a scale so small it's nearly unimaginable. At this tiniest scale, around 1035 meters, the Planck length, space, and time as we know them begin to break down. What we find is not a smooth, continuous fabric, but something wild and chaotic, a frothy, bubbling sea known as quantum foam. Coined by physicist John Archibald Wheeler in the 1950s, quantum foam is a concept born from the effort to unite two great pillars of physics, quantum mechanics and general relativity. While Einstein's theory describes gravity and the curvature of space-time on a cosmic scale, quantum mechanics governs the strange behavior of particles at the tiniest scales. Quantum foam lies at the intersection of these worlds. In the traditional view, space-time is like a smooth sheet. But according to quantum foam theory, if you zoom in close enough, that sheet becomes turbulent and unstable, like the surface of a boiling liquid. Tiny fluctuations in energy create virtual particles that pop in and out of existence in mere moments. These microbursts give space-time a dynamic, ever-changing texture. This foam isn't just an abstract idea, it could have real consequences. If space and time themselves fluctuate at the smallest scales, they might subtly influence how particles move, how gravity behaves, or even how information is stored and transferred in black holes. In fact, some scientists believe quantum foam might help explain the black hole information paradox, or how black holes interact with the laws of quantum mechanics. Quantum foam also plays a role in our theories about the early universe. Just after the Big Bang, the cosmos was incredibly hot, dense, and chaotic. In those first moments, space-time may have resembled a turbulent foam, fluctuating wildly as the universe began its rapid expansion. These fluctuations could have laid the foundation for the cosmic inflation that followed, possibly planting the seeds for galaxies and large-scale structures we see today. From a theoretical perspective, quantum foam challenges our understanding of reality. Thanks to the Heisenberg uncertainty principle, we know we can never simultaneously know both the exact position and momentum of a particle. Similarly, at the quantum scale, we cannot define space-time precisely. It is inherently uncertain, restless, and in flux. Some experimental physicists are even looking for indirect evidence of quantum foam. They study high-energy cosmic rays and gamma-ray bursts, hoping to detect tiny distortions in their paths. Distortions that might be caused by space-time's foamy texture. While quantum foam remains a theoretical concept for now, it represents a powerful idea that the very foundation of the universe is not stable or fixed, but dynamic and alive. It suggests that space and time are not just passive arenas where events unfold. They are active, fluctuating players in the grand story of the cosmos. As researchers continue probing the depths of physics, quantum foam stands as one of the most exciting frontiers, where the laws of the very small meet the forces that shape galaxies. Understanding it could unlock new insights into gravity, black holes, the origin of the universe, and the fundamental nature of reality itself. Einstein changed everything when he showed us that space and time aren't separate. They're one thing: space-time. Massive objects like stars and planets don't just sit in it, they bend it. That's gravity. Time even ticks slower near strong gravity. This is general relativity. But zoom way in to the tiniest scale and everything changes. At the Planck scale, space-time isn't smooth. It's chaotic and unpredictable, bubbling with energy. This is quantum foam, a wild idea from physicist John Wheeler. It says space itself is constantly fluctuating due to quantum energy. Virtual particles pop in and out of existence, making even empty space come alive. This quantum chaos doesn't fit with Einstein's smooth curves, and that's the big problem. Relativity and quantum mechanics don't agree, but quantum foam might be the missing piece that unites them. It could help explain black holes, the Big Bang, and why the universe is structured the way it is. In short, the universe isn't calm and empty. It's a storm of energy and fluctuation, even at rest. And quantum foam may be the key to unlocking the true nature of reality. Quantum foam, a term introduced by physicist John Wheeler, describes the strange, frothy nature of space-time at the smallest possible scale, the Planck scale, about 1035 meters. At this level, the universe isn't smooth or stable. Instead, space-time constantly fluctuates, bubbling with virtual particles that pop in and out of existence. These tiny fluctuations mean that particles might not have fixed positions or momenta, leading to bizarre quantum behaviors like superposition and entanglement. This chaotic